this is recording now. Is that right? Right. So there are future seminars coming up on 11th of October and 15th of November, same time. I think they're Mondays. So hopefully you'll be there to join us on part 2 of storage and also expert design, installation and maintenance issues. So looking at controls and performance gap and things like that. So tonight, oh, happy solstice, by the way, everybody. On the 21st of June, we are on. We've got 3 amazing speakers, Manuela de Castro, Chris Roberts, and Wolf Freur. And we are going to talk about storage in its varieties, all the way from passive to active, all the way to supply and demand issues. So covering quite a wide spectrum of knowledge. So it's going to be quite interesting, hopefully, and cover a broad brush kind of start of the storage issue. To start us off is Manuela de Castro. Nella's a researcher in architecture environment, interested in passive and low energy architecture and sustainable energy technologies in building. Manuela worked as a researcher in Glasgow School of Art on a fabric integrated thermal storage project, but recently with the University of Bath, she developed ShellTherm, a thermal assistant design tool for shelter design. She'll start this session by showing us a range of active and passive storage methods, what she calls taxonomy of storage, the background understanding of heat load management and all that sort of stuff, and how different materials and fabrics respond to storage as well. So Manuela, if you would give us a start, that'd be great.
I need to share my screen, yes. Shall I start now to share my screen? Okay, yeah, and yeah. I hope you are all seeing the screen. So I'm presenting thermal storage in buildings, presenting my work on storage and concepts in materials and fabric integrated thermal storage. So this was the work I did a few years ago at Glasgow School of Arts with Strathclyde University, University of Bath and Imperial College of London. So today I will show my work on the taxonomy of fabric integrated thermal storage, the concepts we developed, and the construction materials we had to identify, or we identified that's suitable for this project. So the last 2 ones, the concepts and the materials were done in parallel. So I divided it in here, but I hope it makes sense how it is. If you have any issues, then ask me later. So I hope you're not lost with all the terms. How we use terms and concepts that might be new for you. At least some of them were new for me when I started working on thermal energy storage in buildings. So before we start with this content, I'll make just a brief introductions to storage methods and systems. So we have 3 different ways of store. Yeah, you okay? We have 3 different ways of storing energy. It can be sensible heat storage, latent heat storage. So both of these are physical methods. And we also have a chemical method, this thermal chemical storage. In this presentation, we'll focus on the first one, the sensible storage, thermal storage. So these designed options for these sensible thermal storage systems, we have, for example, a surface as a heat for the heat transferred. We can have free conduction or convection, and this is a passive storage system, or we can force a convection. And if you do that, we start immediately to have an active storage system. the heat transferred with the heat exchange, and we also have heat transfer that takes place within the same medium, for example, a water storage tank. Now, for active storage systems, there are several options for what fluid we can use and what system we can use to charge and discharge a storage. But as we can see in this image, the options that we have are dependent on the storage temperature. For example, greater is the temperature range of the storage, the reduce is the way that we have to charge the storage. So I hope now that we have some concepts or some terms that we can, we will move now for the fabric integrated thermal storage. At the starting point of our work, the initial question was, how can we integrate the thermal storage into the building fabric? So we start mapping where could we store and how could we store the thermal energy. And we look at four main things, like the location, the type of materials, the type of...
Is this on till 7 o'clock?
And the type of temperatures. And this is how the mapping starts to look like. For the locations, we look into structural elements as, for example, floors, roofs, external walls, or foundations. We look at internal elements as partition walls, but also internal areas or voids, like, for example, in, around, or below stairs. The systems were defined as couple of decouple, and this is linked with the storage temperature, which is divided for ambient, low, medium, and high. So the systems will be passive, hybrid, or active. And again, it's dependent and is organized according with the storage temperatures. Now later, we cross this information, this taxonomy, with previous taxonomies, also with a literature review. And this new taxonomy of fabric integrated thermal storage, we start to find the locations and the systems that we could use, but also we can start to see the areas that we could explore. Most studies we found were coupled systems with ambient and low storage temperatures, and coupled systems would include passive but also active systems. And we notice, what we noticed was that most of the studies would use air or water as the heating fluid, and a really reduced number of studies would use electricity. When we move to higher temperatures, we found that greater the storage temperatures, the fewer are the available studies. So the systems are decoupled with the living areas, and we found that we had less options for the location of the storage, but the potential of new studies were higher or greater because there was a lack of studies with thermal storage in buildings with higher temperatures. So by moving to higher temperatures, the potential of storage capacity increased, but we also noticed that we would have additional research to do. And it was about how could we design a storage with higher temperatures without overheating the space or the living spaces. So now I'll start the concepts that we develop and try to explain how we did it. So after the taxonomy, we came with a list of concepts, and we start from higher temperatures to ambient temperatures. Most of them we use solid sensible storage. Some of the initial concepts we use electricity to direct charge the storage, while others we use heat pumps. Depending on the storage operative temperatures and the concepts, they are either coupled, semi-decoupled, or decoupled from the living areas of the building. So from the initial concepts, we end up with a list of the final ones. And I tried to go through each one of them briefly, but with enough details for you to have an idea of each one. So the first one was, the concept number one was the ground floor slab, so foundation plus slab, solid concrete high temperature storage that is decoupled from the building internal areas. The storage is charged with electricity using a resistance that is within the concrete storage. The heat is retrieved with the heat exchange, so it's a air pipe system that is in the top of the storage. For the ventilation storage, this is again a concrete storage that is charged with electricity. It works exactly as a storage heater. So it's semi-decoupled from it's a semi-decoupled storage. The heat is retrieved passively or actively. So if we require, we can use air vents or fans to increase the heat transferred. And we had the option to have it as foundation slab storage or wall storage. Now the third concept, so it's a horizontal thermal labyrinth, is a solid storage decoupled or semi-decoupled from the living area. The storage is charged with a air-to-air heat pump, and we could use it to store either heat or cold. And it's charged with forced air as part of the ventilation of the building. The concept number 4 is a vertical thermal labyrinth. And in here we have a solid storage semi-decoupled with the living areas. And the storage is charged with force heated air. So we have like 2 coils, one on the top and one off the bottom or at the outlet point of the storage. And we use these coils to increase the air that goes through the labyrinth. And if it requires air is not enough or hot enough, and we require higher temperature, then we can charge again on the basic point. The concept number 5, it's a solid storage with heat pump, and it's a decoupled storage system with low and medium operative temperatures. We built 2 versions of this storage. One was built by the University of Strathclyde, and it was a concrete slab storage. So Chris, if you want to speak about this, have to go on, if you have details that you want to share. And the second demonstrator was a vertical one, so it was a wall, and it was built by the University of Bath. But instead of concrete, they use clay as the storage material. The concept number 6 is a liquid storage with heat pump. It's a vertical liquid storage with active charge and discharge. And it's based, the idea is nothing new. The new thing about it, it was based on a commercial model storage container that is completely flat and could be modeled to be like a wall. So it's about the design of the storage. So the storage is charged with a heat pump, and we can either use a radiant floor or radiant wall to distribute the storage heat. Concept number 7 is a thermal mass activation, and in this case, the building fabric is the thermal storage. It's a low temperature storage that it's coupled. So we have a heavy constructive elements that are exposed to the living areas, and their mass is activating using the building heating and cooling system. In here, what we are doing is we are overheating or underheating the building to reduce and shift the peak loads. Now, the last one, concept number 8, is a ground storage. And it's ambient and low temperature storage, and we use 2 systems, or we use 2 thermal storage. One is below the building, so it's a below ground storage. And the second one is a solid storage coupled with the living area. So both storage are charged with the ground source heat pan, and we can either use it for heating or cooling. So for each one of these concepts, what we did after was going through the details of each concept and the implementations, the possible implementations for these designs. So for the details, we look at things like, again, how the storage is charged and discharged, the storage temperatures, what type of applications, can we use it for heating, can we use it for cooling, is there any way of using this system for also, for example, domestic hot water, and the materials, the construction details, what type of storage materials and insulations could we use. And also for each concept, we look for the implementation. Where can we implement this system? Again, we look at different type of houses types. So we look at detached, semi-detached, flats and terrace. We look for different size of storage, which are linked to the storage temperatures. So it could be a small storage, a medium, or a large one. And this is the example of possible positions for ground floor slab. Now for vertical fabric integrated storage, we look also for the possible storage positions based on the different type of houses, based on the size of the storage, but also on the type of wall. It's internal wall, is external, is a party wall, and so on. So now I'll be moving to the last part of the presentation, that is about the materials that we use for feeds. How do we select it? So when we start to generate the concepts of feeds, I produced this diagram with the help of my colleagues at StartClyde, and this was like a tool or a guide for me. So I could easily identify which systems and working fluids we could use when I was designing the concepts. But at a certain point, we start to question how far could we go with the storage operative temperatures. So we went up with upper limit of 750 degrees Celsius. So now, how did we come up with these values? We look for different storage systems that we normally use in buildings. And this is the value that the core of a storage heater can reach. So based on that, I'll increase the whole table or diagram, and I try to find out, based on this large range of temperatures, what were not just the fluid and the systems we could use, but also the insulation and the storage materials. So we did a literature review on insulation and storage materials. And we end up to focus, for example, this is a review of this is a diagram of the compile information of a review on insulation. And the things that we look at was, or were interesting for the fabric integrated thermal storage, was where these materials are normally applied, the materials service temperatures, so specific at the maximum service temperatures, and details such as, for example, flammability, toxicity in case of fire. So can we use it for higher temperatures? Is it resistance for water? This is if you're using charge and discharge fluid as a water. And is it resistant to loads? Can we use it under a really heavy storage or not? So based on the set list of objectives and requirements for fits, we used the CIS selector to identify storage and insulation materials. For the storage materials, we use filters as price, as CO2 print, and we come up with our lists. And from this list, we found that concretes and cements are the best group of materials for feeds. This is because they have the great service temperature range, and some have the highest specific heat values and also the lowest price. So this was basically why they are in the top. Now there are other materials that are not coming in this list, and most of them because the CAS selected that we use is the educational version. Now, another type of materials that we find as a good alternative were rocks. But any one of the materials that we find in here are in the top list of the ones. For the insulation materials, the filters that we use was thermal conductivity, fire and water resistance, and load resistance. So the orange ones were the ones that were not included in the CAS selected database, but we got them from the literature review, and we were specifically interested in including these ones. And we come up with the two main groups, the inorganic based materials and the organic based insulations. And both of them will have pros and cons for the fabric integrated thermal storage. The organic based ones are suitable for a large range of temperatures. So they can operate from ambient temperatures to quite high ones. They have the lowest prices. They are suitable to be used under really heavy loads. But they have the highest thermal conductivity values. On the other hand, the organic-based materials are limited to low temperatures. Some plastic-based materials have the highest prices. Not all of them are suitable to use under heavy loads, but they have the lowest conductivity values. So it's kind of a mixed thing. We end up, for some concepts, we end up not having a specific insulation or material, but you have to combine different materials. So this is what we end up together, and this was the diagram that I end up using when I was developing the details for the concepts. I'm finishing now the presentation. I hope it was useful. Chris, I don't know if you want to add anything to this presentation. Yep.
That's great. Thanks, Manuela. Wow. So much information there, so dense. I'm glued to my screen going, oh, well, what? I just want to say also that there's a Q&A at the end. So if you could all write your questions into the chat before you forget it, I'll try and cover as many as possible at the end after all three speakers has spoken. So now I'd like to invite Chris Roberts to speak to us specifically about batteries, about its installation standards, as well as how it works generally, and calculating self-consumption of use of battery with PVs, or whether it's good to use it with or without, and how we work it all out. So Chris has been in renewable energy in the industry for like over 20 years. And he's one of the original founders of Microgeneration Certificate Scheme, the MCS, in 2006, which now determines the minimum technical standards for small-scale renewable energy installations in the UK. Chris's involvement in the industry has been varied from chairing technical working groups, authoring standards, and serving as executive director for many companies in this sector. So over to you, Chris.
Lovely, thank you, Glo. Yeah, so hopefully most people will be aware of MCS. If you're not, if you've got a solar PV system on your roof, or you've got an air source heat pump, I would hazard a guess that your installation was undertaken by an MCS certified contractor, and you've probably got an MCS certificate for your installation. We've currently got something like 1.3, 1.4 million installations registered with us. That's probably about 1 million solar PV systems in the UK, and probably about 300 or so thousand air source heat pumps registered in the UK. The scheme, as Glo's mentioned, was originally conceived of in 2006. It now underpins almost all government incentives, including UK government incentives and Scottish government incentives as well. And effectively what we do, we set the technical standards for the industry and allow the certification of installations and products. I'll also add that I'm currently talking to you from not so sunny Leicestershire, but in 2 weeks' time, I do move permanently to just south of Oban. So I am joining you all up there in sunny Scotland. So you might well see a little bit more of me in the months and years to come. So I'm going to share my screen. It's a relatively high level presentation. So, and it's really covering off, as Glo's mentioned, battery storage systems, what we are doing in terms of battery storage systems, developing technical standards, and really probably giving you a bit of a feel for where we see the market is going. So I'm also going to try, which I've never done on Zoom before, is try and use my pointer. So I don't know whether this will actually work. So I'm going to use a laser pointer. So hopefully you might actually be able to see that laser pointer there. So I suppose firstly, just to get a bit of a feel for the market, my presentation is more at the sort of the commercial deployment sort of end. I think Wolf's going to go through things in a little bit more detail in a little bit, so I might dig into some of the issues that I sort of gloss over a little. But why is electrical energy storage becoming more and more important? Well, hopefully, well, many of you may already know this, but our electricity generating system and distribution system probably dates back to the 1930s, 1940s. It's very much designed around large centralized generating stations, and then a series of transformers and wires that gradually get narrower and narrower and narrower as they carry that electricity to our homes and businesses down here. But there's a few issues with it. It was never designed for electricity to actually flow backwards, so it struggles to actually deal with that. And it also has what's called very high spinning inertia. You may or may, well, I'm sure you all know that our electricity system is an alternating current system. It's based on 50 hertz frequency. That frequency is a function of giant generators spinning at a particular speed to generate that frequency. And as we retire big coal-fired power stations, that spinning inertia is in decline, which means that the frequency is starting to wander a little bit. And that's very problematic, because if we deviate too much from 50 hertz frequency, then all of our electrical devices start to get a little unwell and start to sort of fall over. So that's one of the main issues. And as I'm sure you all also know, that we're requiring more generation and more network capacity as well. We're using more electricity when we're looking to use more electricity to heat our homes. We're also looking to transition across to electric vehicles as well. So actually the demand for electricity is rising rapidly, and faster than the generation is rising. And we've also got more distributed generation, so more wind and solar. And as I've already said, they push or try to push the electricity backwards through a system that wasn't designed to allow electricity to travel backwards. So what we're starting to see is what we call stress events becoming more common, which can be brownouts and blackouts. Thankfully, they've been relatively small in number, but they do occur occasionally. There was a big event, I think it was last autumn in the southeast of the UK, when a lot of the system, there was a bit of a domino effect. A lot of the switch gear and systems on the system just basically tripped out in succession, and it caused quite an issue. There are a lot of power outage for a good few hours, and they're likely to become more common unless we address it. So the age-old solution would have been to build new centralized flexible power stations and upgrade the network for peak use. But the problem with that is it costs billions. We're in a competitive energy market, and therefore the amount of spare money sloshing around in the system to invest in big new power stations and upgrading the distribution and transmission network is limited. Nobody really wants to pick up the bill. So the alternative solutions, and this is where electrical energy storage really starts to play a role, is we need to look at creating a smart network. And that's where we can, through the use of smart devices, start to manage supply and demand in a more efficient way, which obviates, sort of mitigates the need to start to upgrade the grid, because we manage peaks and troughs, and this is where batteries can play a role. And batteries can allow National Grid, who manage the whole system, to procure balancing services. So rather than switch on or keep a coal-fired power station spinning in reserve, they can draw power from battery storage systems instead. So when there's an excess amount of generation on the grid, they can charge the batteries. And when there's a deficit of generation on the grid, or when there's a peak demand, they can draw power from the grid. And they can also use that to manage the frequency. And as I say, encourage virtual capacity, which is demand side response. So with a mix of asking large energy users to turn up or turn down demand, they can use batteries to do the same thing. And that gives us a whole host of benefits to consumers. And we're more, from an MCS point of view, we're more concerned with residential domestic. There's a lot of large-scale battery storage starting to be deployed around the country. But our interest is primarily at the consumer level. And the benefits for those, and it is growing rapidly. The main thing being is it increases the possibility of self-consuming or self-consumption of the electricity that people generate with a solar PV system. I'm telling you the obvious, but we know solar generates more during the day, around midday, and that's when a lot of people tend to be out at work. Although, of course, that has changed in the last year, 18 months, where more and more people like me are working from home for 90% of the time. But in terms of improving that self-consumption, it therefore also improves the value of solar. We no longer have feed-in tariffs, which drove deployment and drove demand for residential feed-in tariffs. So without that now, battery storage can improve the financial returns consumers benefit from. Although it's probably important to caveat that at the moment, it still doesn't stack up financially on its own, but it's beginning to as battery storage prices do start to come down. Consumers can also benefit from arbitrage. There's growing use from some electricity suppliers for time of use tariffs. Some of you may know of Octopus Energy. They've got what they call Octopus Agile, and that's a half-hourly tariff where the retail price of electricity can vary quite rapidly throughout the day. But more importantly, it's at its most expensive between the peak hours of 4 and 7 o'clock. And then it can go very cheap in the early hours of the morning. And in some times of the year, it can actually go negative, i.e. people can be paid to use electricity. And this presents an opportunity for people to use battery storage to charge the batteries when they've got lots of free electricity, or cheap electricity, either because of time of use tariffs or from solar, and then discharge those batteries during the times of day when buying electricity would be far more expensive. You've also got island mode, i.e. the battery storage systems can provide power to house during power cuts, although that needs to be used with caution. Technically, it's quite challenging to make sure that the system is safe, because in the event of a power cut, a lot of our homes actually are earthed through the incoming electrical supply, and if you try and run a battery or a house in island mode, and you've lost that earth, which is provided by your distribution system, then it can be quite hazardous. So that's something with caution. But a lot of people do like to think they can have a battery storage system which gives them power during a power cut. Easier said than done. And finally, there's potential to access ancillary services I've put here through an aggregator of virtual. VPP stands for Virtual Power Plant. So I've already mentioned that the likes of National Grid will look at buying services that can be provided from battery storage systems that help them balance the grid. What they don't really like doing is contracting with hundreds or thousands of small systems or small homeowners. They tend to like to deal with big systems, big providers of those services. But there is an emerging market now for organisations who will aggregate, who will actually control centrally hundreds, if not thousands, of battery storage systems. And collectively, they will add the capacity together, and then they will collectively use those systems to bid into national grid to provide those services. And there can be revenue generating opportunities that they then share with those customers. So those are the sorts of the benefits, but the primary ones are the top two. Increases self-consumption of solar. So from an MCS point of view, we decided to develop a standard to cover the installation of battery storage systems back in 2019. And this is a standard for the installation, and we would look to certify installation contractors. So I've already said, if you have a solar PV system that you want to be installed on your house, the likelihood is you will go to an MCS certified contractor to do it, because they demonstrated their ability to work to the best standards in the industry, and they have the competency to do the work. But why did we look at doing battery storage systems or a battery standard? Because historically MCS was all about renewable generation. So solar PV generates electricity, wind turbines generate electricity, heat pumps, they generate renewable heat, or they extract it from the atmosphere. So this was the first time we looked at doing storage, but two main reasons. One was convergence with existing technologies. So as we talk about smart grid, all of these technologies, including solar PV, heat pumps, batteries, they'll all start to converge, and they can all be used in an intelligent way to help us actually manage the capacity that we have on the grid. So that's convergence. And also safety. With batteries, we're potentially talking about a huge amount of energy compacted into a very tight space. And if that's not done in the right way, or if the product isn't safe, or it's designed incorrectly, or installed incorrectly, then there is a potential for a huge amount of energy to be released very quickly. And another name for that is an explosion. But I don't want to, obviously, you'll have to excuse my dog. The perils of working from home, but obviously I don't want to fearmonger there. Most products are very safe, but it is a small risk if done incorrectly. So that was one of the reasons we wanted to start to develop standards to start to wrap around the industry. There was also the issue about mis-selling. So this was one of the main reasons that MCS was conceived of and launched in sort of 2006, 2007, is because these technologies are unfamiliar to most of the general public, so they don't really know what to look for or how to identify a contractor that knows what they're doing, what a good system looks like, or how the benefits should be presented to them, so they're not exaggerated, so consumers can actually make an informed decision. So by developing our standards, which are publicly available for free, you can go to the MCS website and you can download them. There's no charge. You can see for yourself what standards we expect our contractors to work to. And we also have a partnership with RECC, which is the Renewable Energy Consumer Code, and they help to govern the way contractors sell and market their wares. And thirdly, we built a methodology, which is something that MCS does fundamentally with all its technologies, is we build a methodology for that contractors must use when they're trying to sell the benefits of these technologies to their customers. It prevents them from exaggerating the benefits or the energy that will be stored or generated, and prevents an arms race from one salesman saying that his system will generate or store more than the next man, without justification for that. So that's why we developed the standard. At the moment, it's worth saying we develop our standards with technical working groups, which are populated with people from industry as well. So MCS doesn't actually impose the standards on industry. We work with industry to articulate what they want to see in terms of a technical standard, and then so we put it into writing. Initially, we decided not to do a product standard. Most of our technologies, say for solar PV, we have a standard for installation and a standard for the PV modules themselves. Or if it's for heat pumps, we have a standard for installation, a standard for ground source heat pumps, air source heat pumps, and in terms of minimum efficiencies and all sorts of requirements. We decided initially not to do product standards because a lot of the product 2 years ago was quite good. We are starting to see some products which are less good. And so we are now considering actually developing product standards around that, so we can make sure that the only products that bear the MCS mark, that logo there, do meet minimum safety requirements. And we're proud to say, I think our standard, it's snappily called MIS 3012. That stands for Microgeneration Installation Standard, and then our reference numbering system. To our knowledge, that was the first installation standard anywhere in the world. The plan from now, there's a picture of the sort of thing that we were looking to avoid. Here's an installation that I came across doing some of my other work. I do a bit of expert witness work and site inspection and this sort of thing. And this was sort of a rather poor quality installation that we came across of a battery system. You can see the wires there are an utter mess. They don't even comply with basic wiring regulations. The battery itself is just supported on the loft floor. It's not properly supported. The marker pen used on the inverter as user instructions. It's just very poor indeed. And these are the sort of practices that we're actually looking to address. I'll come back to that. In terms of progress, we launched our battery standard actually at the beginning of 2012. Sorry, not 2020, sorry. With a view to certifying the first contractors throughout 2020 on a pilot basis, and then launching commercially as a certification model back end of last year. But then, of course, in sort of March of last year, we were hit by a certain unexpected event called COVID, and that sort of delayed our whole implementation. So at the moment, although we do have a battery standard, you can't find an installer that's been certified against it, but we're hoping that that will start to happen this year. I mentioned energy calculation, and Glo mentioned that we developed a methodology, which we did. It was developed in partnership with the University of Loughborough. I won't go it through detail, but I'll show you where you can find it if you're interested in downloading it. Again, it's a freely available document called, again, snappy title, MGD003. And basically what this document does, it's applicable for domestic scenarios with electrical energy consumption of 1,500 to 6,000 kilowatt hours a year. And using archetypes, various archetypes, which is homeowner occupancy. So you've got home all day, out all day, i.e. at work, home in the morning or home in the afternoon. It works out, it gives an approximation for the amount of electricity that a home would self-consume generated from solar, depending on the size of the solar system and their electrical energy consumption, with and without various levels of electrical energy storage. So for argument's sake, its self-consumption is capped at 95%. So for argument's sake, we may have a typical home where everybody's out all day. They might have, say, a 3 kilowatt solar PV system on the roof. If they don't change, if that home or household doesn't change its behavior at all, we might expect them to self-consume probably 30 or 40% of the solar generated electricity that's on their roof. With a bit of modification to their behavior, putting, say, the dishwasher or the tumble dryer on during the day when the sun's shining, they might be able to get that to 40 or 50%. But then if they actually put a battery storage system, depending on how big that battery storage system is, then they might be able to get that to 60, 70, 80%. But this methodology allows for that to be estimated. Basically, this process map is in the battery standard MIS 3012, and it talks about how to actually calculate it. So firstly, determine the services to be provided by the electrical energy storage system, whether it is to drive self-consumption, only self-consumption, whether it's to be used for no self-consumption at all, i.e. other purposes, or in most circumstances, if it's to be used for both. You allocate the proportion to the different services, and then you calculate the method. It was quite complicated working this out because, of course, batteries can be used for so many different things. I've talked about self-consumption, I've talked about ancillary services, I've talked about backup in terms of a power cut, but in reality, most consumers will use the battery for several different things all at once, and this is all about allocating the proportion. That's that in a nutshell. Yeah, so where are we at? Next step. So I've already mentioned this. So we were doing the trial assessments with 2 of our certification bodies. So the way MCS works is we set the standards and we set the sort of infrastructure out for certification, but then we work with certification bodies who will certify installers. One is NIC, EIC, and one is NAPIT. The idea being that once we did those trial assessments last year, I've already said that COVID has delayed that. We would update MIS 3012 based on the feedback that we get and the findings we find in the field. We will then update MIS 3012 and then say full certification. We now think it's down towards the end of 2021 because of that delay. We have developed training for contractors, so there is now a training course that they can go on. We're now thinking we'll develop a product standard. I've already mentioned that we're starting to see some product enter the market, which is probably not of the standard that we would hope. And we're also looking to develop some requirements around those aggregators. So organisations who will create virtual power plants by contracting with, say, 1,000 homeowners and their batteries. But the devil will be in the detail with that, because the nature of the contracting arrangement could either benefit those homeowners or disadvantage those homeowners, particularly if they've paid a lot of good money for an expensive battery storage system that they find out somebody else is using 90% of the capacity. So that's it. But before I say thank you, I'm going to stop share, and then I'm going to show you. I did say where you'd be able to actually find those.
I've posted the MCS link to everybody.
Have you?
But I don't have the one to the calculation of consumption one. So if you could post that, that'd be great.
Yes, I will post a link now.
Yeah, as we're running slightly behind. While you do that, I shall introduce Wolf, if you don't mind me doing that. So our next speaker up, Wolf is from Heriot-Watt University. And he's going to tell us something about the supply and demand and, control of weighing it up for renewables. Whoops, just lost the script. Excuse me. So Wolf's background is in atmospheric physics and focused with geophysical fluid dynamics, and now teaching fluid mechanics and energy technology and renewable energy at Heriot-Watt University. His work initially was on wind turbine aerodynamics and wind energy resource assessment, but recently he's more interested in the integration of variable renewable energy sources, including marine and solar energy, into the system. So his particular interest is studying the optimum design for hybrid systems and advanced scheduling of energy storage devices. So obviously it's to our interest to hear about how it all is all put together in supply and demand. And I'll hand it over to Wolf, if you would guide us through that.
Thank you very much. Can you see my slide?
Yes.
Good, and you can hear me. Very good. Right, I'm Wolf Früh, and thank you very much for the introduction. So yes, I'm a complete outsider. You don't see any word sun, solar, PV below the title. So I'll talk more about what to do with the energy coming out of your systems. So I just structured my presentation into 5 main sections. First, giving the context, which you can put back into the context of Chris's and Manuel's presentation. Then try to pinpoint the challenge I want to address, explain how we can look at that with my modeling approach, and then give you 2 examples of applying that to 2 very Scottish examples. Right. The context, we all know that solar PV and solar thermal installations are mature technology and widely installed, from device-emitted PV cells via domestic PV and solar water heating devices, which Chris covered in detail, to utility-scale PV farms. And electricity storage has long been the most expensive part, but recently the prices have been dropping quite fast, much faster than price for actually PV systems, for example, have dropped. And we've now got sort of a range of mature and emerging technologies for a vast range of services. Remember, Chris talked about the inertia of the electricity grid, the fact that we've got tapering infrastructure, so and ancillary services, arbitrage and self-consumption. Those are all different usages of the energy storage systems. And also the same now is emerging for thermal storage. So we're going actually beyond building integrated thermal storage for keeping houses warm, also to water tank, but also for thermal storage for industrial processes, phase change material batteries, high pressure steam vessels, whatever. So it's a quite an active market or field. So how can we use the storage technologies to make best use of low carbon energy sources? That's really what we want them to do, apart from reducing costs. Especially for solar, we all know that we've got the daily cycle. Sun hopefully rises in the morning and might set in the evening, and also an annual cycle. And that is a big problem when we come to looking at self-consumption in cases where the heat provision is also electrified. So there's a move towards electric heating. We need loads and loads of electricity for heating in the winter and much less in the summer, but we get much more solar energy in the summer than in the winter. On top of that, we've got irregular variability from the seconds to hour time scale. Some things we need to sort of keep an eye on to cover this problem. Chris talked about the inertia which was built into the electricity grid by the big power stations and is now disappearing, and so the grid becomes more susceptible to tripping up over frequency issues, and also riding through weather systems when we might get less sun or less wind. So storage is a method to smooth out those cycles and these irregular variabilities. But then the question comes, how and how much does using a certain storage technology actually affect the productivity of the original source of the electricity or heat? And what what are the opportunities we can exploit, and what are the challenges we need to address. And those are more so system challenges than safety challenges. I mean, they are absolutely important to have the safety certification, but here in my talk is really looking at sort of the system balancing from a fairly sort of technology neutral point of view. So I want to now take things back to the key information which we need to have and use to meet demand at the time when the user wants it. So we've got the user, and for that the user has got a certain demand, and in a model I can either measure it or create it. Given that PV and all renewables really are highly location specific, we need to know where they are, how much space, roof space or garden space they have for budget, and also what is their grid connection like. Remember, the tapering of the distribution grid means if you're at the end of the grid, you've got a fairly thin wire, and you can't import much, but usually you don't notice because you don't want to, but also you can't export much. Usually your export is probably more limited than your import. And also, if you want to use arbitrage, what are your grid tariff options? What are sort of time of use tariffs available? Then we sort of turn around 180 degrees and look at the resource data. So we need to look at the sunshine and the wind speeds, and we can get those from national or global databases. And so the standard is that you only get it to about hourly resolution. So you might need to do a bit of not downsampling, but upsampling to fill in gaps and select the range of possible devices in terms of how do they typically respond to sunlight or wind, and then how much does it cost you. So this is information I would put into a model to figure out what can batteries actually do to help the user to get most out from local energy resources. And for that, we also measure actually what is the best use. What do we want? Do we want them to be self-sufficient? Do we want them to reduce carbon footprint? Or is it purely a cost-saving exercise for the investment they need? So that's where we need to use the mathematical term of objective function. So what's the objective of my system design? So we need to find the configuration of generation devices, be that PV, solar thermal, wind, ground source, heat pump, or whatever, which gives the best performance overall. And now I've created a model which puts all this together, and I've sort of created sort of a graphical picture of that model. So we've got the demand on the top left. It's a weekly line going so for a week in this case. Monday is on the left, Sunday is on the right. And this is actually a measured demand from an industrial client, so medium-sized. And on the right, we've got the wind speed data for that location and the solar irradiation for that location. So now we need to start bringing those two sides of the problem together. And first of all, choosing a wind turbine and choosing a PV panel, we turn the wind speeds and the sunlight into electricity, wind power and PV power. So this picture is, I drew for electricity alone, but there's no reason why it couldn't be sort of a dual system for electricity and direct heat. And then, of course, the problem is how many wind turbines, how many PV panels do we need? So number n, and then how many batteries do I need, and what are my sort of hardwired limits within which I can sort of actually develop my or install my system. So I multiply my wind power from one turbine with the number of turbines, hopefully, number of PV panels I can afford, and then put that against the demand to look at the imbalance between those two. So in this residual demand curve, the red bit above the zero line means I do not have enough renewable energy to meet my demand at the time when it's generated. And the blue troughs below the zero means I produce more than I need. So we always have either too much renewable or not enough renewables. If we don't, can shift it in time. Right, so batteries can take surplus generation and then shift it in time, and release it when we've got deficit. How much batteries do we need, or is it actually cheaper, better, more effective to import from the grid or export to the grid within the given limits, and then having made that decision using some clever algorithm, we sort of activate the battery storage use, we fill it up or drain it, account for some charging or discharging losses to see how the level of charge in the battery goes up or down. So the rightmost green picture at the bottom right. So we start with an empty battery. There's not enough renewable power, so nothing happens much. And then on night of Tuesday to Wednesday, the wind picks up and I can start charging my battery. And then later in the week, it drops down again and we can discharge it and meet the residual demand. And then for the rest, I can import, export to the grid, and also might need to actually curtail or throw away any surplus generation which I can't feed into the battery or into my grid. So this is a picture of the model I'm going to apply now to two examples. Next example actually includes wind, PV for both heat and power demands of a highly idealized distillery using a batch distillation, so 1 batch a day for Monday to Friday. And it's located in the, not far from where Chris is moving to, so west coast of Scotland, an island there. And I want to use the local solar and wind to reduce the electricity consumption of that distillery. And for the heat demand of the still, or 2 stills, I'm going to use a phase change material heat battery and a normal battery for the electricity demand, store surplus generation, use and store that, then use that for self-consumption, and then use the remaining storage capacity to charge at night. So that's the arbitrage. So the first bit store surplus generation is self-consumption. Second line to charge at night is the arbitrage of actually making use of cheap electricity and shift the forward time to when everybody else wants it is more expensive. And that means that my electricity and heat demand, we were just saw these blue and red lines, are now filled with the shaded bits. So shaded bits here, where I can actually use my PV and wind to supply electricity, and also there, so you see, so also this to meet heat demand there. This turquoise bit is I've got more generation than I need, so I can use that for storage and then supply the heat demand the next day with that. And the results of that is, so what I'm going to show you now is the percent or the amount of locally produced PV electricity as I increase the size of PV panels. And just to put it in numbers, my average demand is 1 megawatt combined heat and power, and with a peak of 3.6 megawatt. And the PV has got a capacity factor of 15%. And if I've only got PV installations and no batteries, as I start putting PV panels onto this one, is PV capacity from nothing to 10 megawatt peak. So this is 10 times over in capacity for the average demand, or almost 3 times peak capacity, peak generation capacity over peak demand. So I start with having, of course, nothing. It goes up. I meet about 40% when my PV panel installation is 3 to 4 megawatt peak. And when I've got 10 megawatt peak installed, I only meet about 60%. It really flattens off. So the making the system bigger and bigger, yes, gives me more self-consumption, but progressively less and less. So there's less added benefit in making the system too big. So there's somewhere you spend lots of money without any benefit if you can't make money from exporting the electricity. So once the PV system size reaches about the peak demand, the curve flattens off. And when it's oversized, you get little local benefit. So I'm now focusing on the local benefit, the self-consumption aspect. And it reaches an upper limit of 70 to 80% for really big. You never get 100% because when the sun is not there, it's not there whether you've got a huge wind PV farm or not. Now, let's overlay on this PV self-consumption a battery system of different sizes. So now we see this black line is the same from before, but increasing battery size of 2, 4, 10, and 20 megawatt hours size, we get a big increase push up of this sort of contribution from here about 60% to maybe 80%. But again, making the batteries bigger and bigger gives us less and less added benefit. So putting some moderate, well-sized battery onto the system gives me a good benefit, and then making it too big means I waste money. This is PV only. And now my other hat comes on, my windy hat. And for wind, the graph, same graph, looks very different. So the wind goes up much more rapidly, but then the actually leveling off is a bit flatter. But we also get better we get better incremental use from bigger storage, but for the PV, the difference between the no storage and small battery was bigger than between wind with no storage and wind with small storage. So the small storage is more effective for PV, whereas for wind, the big storage is more effective. And we can explain that by looking at the seasonal variability of those things. Remember, wind is random, well, fairly random. PV has got a strong daily cycle and strong seasonal cycle. So the strong daily cycle, you put in a battery to cover 1 day's period. Wind, it doesn't have that clear daily cycle, so you need to look at averaging wind over a weather system. And in Scotland, 7 days. And beyond that, again, you sort of lose benefit. And finally, sort of the crowning glory is what do we get if we combine a bit of PV, bit of wind, bit of battery? And there we sort of see that combining all three actually gives us much better benefit. Again, the battery itself only gives sort of benefit up to a certain size, but it's the importance of the three components together, playing the role in covering the different cycles in supply and demand most effectively. So key message from this graph is spread your investment into PV, wind and battery, and size it carefully. Another example, again near Oban, small town at the one end of the Scottish distribution network. This one is purely electric analysis, and it being at the end of the network means the infrastructure is very weak, and we can't invest billions of pounds to make it strong. So there's little capacity to add substantial local generation, but we know Scotland is a sunny country, especially the entire peninsula, and also very windy. So we've got good resources, but very constrained. So what I've again done, looked at the effect of the grid constraint on the usage of electricity, where I sort of looked at different scenarios. One was where I had to be completely standalone, so an off-grid system, or one where the local grid interchange only allowed a very small amount of 100 kilowatts going in or out, 200 kilowatts, or basically something unlimited. And also looked at the difference between import and export. But the key thing, if you now look at the effects of the grid constraint as a number of import and export equal, we see here in this graph, so the bars are sort of a cost estimate expressed as of equivalent annual cost. But key thing is we've got the costs for PV is this orangey bit, the cost for wind installations this, cost for storage the blue bit, cost for gray is backup generator, and the pinkish bit is cost of electricity, and if it's negative, then it's actually an income. In this case, I allowed for some renewable tariff, so you get a payment if you produce renewable electricity, even if you don't export it to the grid. Left column is an off-grid system, so village in the Kintyre or a pod somewhere in the Highlands, and the portfolio of technologies represented by each of those bars is an optimum in cost factor. So the most cost-effective installation for off-grid contains some PV, some wind, some storage, and a backup generator, be that diesel, be that something else. So for off-grid, really, we are looking for the four components of wind, solar, storage, backup. And if we have got a very weak, unreliable grid connection, the picture doesn't change much. If we've got a slightly more, but still much less than what we need, again the same. But as soon as we allow a significant import-export, the picture changed completely. With a good grid connection, it makes no longer sense to have significant backup generation. And also storage doesn't make much sense. There's a tiny bit of blue left there, but most of it is PV and wind, always them together. And then we can start making money by exporting to the grid. That included a feed-in tariff, so the size is a bit optimistic for future installations, but at the time it was still valid. And the last red one was actually the actual electricity costs at the time for 1 year. So all of these renewable solutions save money in the long run, but which one saves you most depends on your grid connection. So key storage. Storage can increase the uptake of renewable generation, but only up to a limit. And that limit is given by the nature of the resource and the storage technologies. And also combining different types of resources increases uptake of renewable. So it's not storage with renewable, but it's storage with the different types of renewables. And the optimum appears to be always a blend of several renewable technologies and some storage. And yes, effect of grid infrastructure, availability of grid reduces the need for storage, ability to import reduces the need for backup, and ability to export can be an income stream. Now, this is all designing systems with perfect knowledge. Once you've built it, and you also tuned your system to be the optimum, of course, the next task is to run it. So one thing which I'm not going to touch now at all, because we run out of time, is we need to optimize how and when to use the different components, the backup generation versus battery, whatever. So for that, we need to know what demand are we expecting, what renewable generation will be available, what the electricity cost will be, and we can do that with some advanced prediction methods where all this fancy artificial intelligence and deep learning comes into play, and also, of course, all underpinned by smart grid technology and capability. And with that, I think I've finished. So thank you very much, and I need to stop sharing now.
Thank you, Wolf. That is brilliant. So just want to quickly say how great that was. Especially the wind and PV storage comparison, that was great. A smaller wind seems to have a much larger effect if you've got a small wind capacity than the solar one, whereas a solar larger system with larger capacity seems to have a bigger impact on with storage. I've never seen that graph before, so that was very interesting. So as time is running very short, all the speakers were so interesting. I didn't want to cut them short. I did ask for a 20-minute presentation. I think they all came up with half an hour instead, but that was all very, very good and interesting and informative. So thank you very, very much. I'd like to ask just a question to, or maybe a couple to each of the speakers, if I may. Manuela, there was a question about whether you are doing practical tests on these different types of fabric integrated thermal energy storage systems in experiments.
They did that for the fifth concept, and I believe that Chris Morgan was designed one of the storage demonstrator. I don't know if he wants to talk about that. So there were two demonstrators that were built. The start quite built the horizontal one, so it's like a slab, concrete slab storage, and the other one is a vertical wall. So they did
Two of the options
on that.
That's cool. So what made you put price as one of the main criteria instead of embodied carbon when you made up your list of materials? Because then it pushed up the concrete and cement quite a lot, whilst we all know that the embodied carbon of that is not so good.
Because this is for starting to be, because this is fabric integrated thermal storage, the price of the material is sometimes one of the things that come up if you are building a house. So if you want to create this type of storage in a large scale, price is going always to come as one of the first choices.
Do you have another list with embodied carbon calculated in?
No, I don't.
Maybe we'll have to look into that.
Because we did especially the storage materials, because we did we use educational version. So we came up with a good, a large number of materials, but I'm sure there are lots of materials that were not included in that list. So I guess we have always plenty of choice to go around and use it. For example, I didn't come up with the clay as a storage material. I in Bath University use it because they have a larger database on the natural materials.
And in terms of the thermal capacity and length of storage and discharge,
most of the studies were done by Strathclyde University. So I think the person who was more in charge of that part of the studies, because it's not just the capacity of the storage, of the thermal storage of the material, is also how long it takes to charge and also discharge. So there are lots of different things that comes with the work. I think it's John Allison. He did quite a few papers on that, just to test it and to see the volume that you require for the type of houses, and also how fast we can charge and discharge. And it was also the same thing with the Imperial College of London. They have also to add into the equations, they have to start also to consider the time that we need to charge and discharge this type of storage.
Hope that answers your question, Rob. So Chris, I think, answered the question on the free standards thing. I think we all appreciate free standards, and that the certifying scheme hopefully will cover the cost of developing the standards. Could you say a little bit more about the island mode and the difficulties of doing that? Because obviously there is something that we need to take into account of in the future in designing off-grid systems.
Well, yeah, it gets quite technical. It depends on the nature of the electrical supply to the building. So a lot of houses in the UK have an electrical supply which is classed as PME or TNCS, which means that the earthing arrangement or the earth is brought into the building with the electrical supply. It's part of the neutral conductor. And earthing of a building's electrical system is an important safety function. It provides for a lot of safety functions. So the problem that you have is if you have a house that is connected on a PME or TNCS system, is if you lose the grid connection, depending on why you've lost the grid connection, you might also lose the earth connection. And that means that a lot of the safety functions, such as you've got in your consumer, you've got an RCD, residual current device, which works on earth leakage. So if you've got no earth, then safety devices like that cease to function properly. So so that's the challenge. So if you were to run a house in off-grid island mode, then you have to provide additional earthing to compensate for the fact that you might lose the incoming earth. So it adds to the cost. So you have to provide an earth spike. And I mean, a lot of houses, I think in Scotland, probably not on a PME, they're probably on what's called a TT, which means you have an earth spike. It's less of an issue there because you can use the earth, you know, the existing earth spike. So it becomes less of an issue. But it just adds complexity, and a lot of the products on the market are not necessarily designed to work in island mode out of the box. So it does require this extra level of competency on behalf of the electrical contractor or the contractor that's fitting it.
Great. Just a quick one on that. I think you responded earlier on the chat about not providing heat battery information just now, but you might look into it in the future. But another question came up with regards to environmental impact of different batteries and so on. Would you think there'll be a standards on that kind of thing, like mineral extraction and processing and that kind of thing?
I suspect so, but that's the sort of thing that would take place at an international or a European level in terms of extraction and the materials. I'm not personally aware of anything that's going on in that space, although I do know a lot of the battery manufacturers are looking to reduce the level of, shall we say, controversial substances such as cobalt from their batteries. And I think as time goes on, they are managing to reduce quite dramatically the levels of cobalt in their lithium batteries. So there's quite a lot of pressure in that area to reduce that.
Yeah, so it's not quite standards as such, but if anybody's missed our last session on LCA embodied carbon recycling, it's quite interesting. Although it doesn't quite exactly cover batteries. The same issues apply obviously in circular economy. That recording is on the SEDA website if you wish to visit. I think there is a question for Wolf on, oh gosh, it jumped. And Wolf seems to have answered it. Would you like to unmute yourself and answer it in person?
Right, so a question, Richard, about costs are going down so much that we can actually simply spend money on building huge PV and wind. And my first answer was, well, we do have to worry about the loss of income from curtailment, or we need to match the excess production with using it for other things. And a lot of research going on actually looking at matching excess renewable generation with things like hydrogen production. So that's a very active area, especially in the offshore wind industry. So a lot of companies looking at that. At the moment, the figures don't add up yet, but we think it's going to be there. And yes, so the main reason why people talk about curtailment is it is a big loss of income, but only should be seen in the context of the capital costs. If PV and wind become very cheap, you don't worry about the lost power, but you still can't build so big that you can't put your stuff into the grid. So it's always a balance between capital expenditure, yield, and putting it on the infrastructure. So yeah, let's go massive, but massive within what can be supported on a sensible way. And also, yes, environmental impacts we shouldn't forget.
Yes. So I just want to bring us to a close and remind you all of our coming seminars yet to come. Storage Part 2 is coming on the 11th of October, where we'll explore more on the grid capacity and the finance and scale and smart options and sort of more in-depth issues for rural applications and urban applications. And expert design in November for, well, design, installation and maintenance, shall I say. It's actually all three we hope to cover. And if you could send me also your suggestions of any future topics you'd like to hear about, we'll try our best to get experts to come and talk to us about it. But I'd like to draw the recording to a close. And